Welcome to Winds Global Systems, Chapter 10, Part 3. Alright, so after today, you should have a better understanding of the role of the jet stream in the atmosphere, another model for the creation of a jet stream, and then some other names for these jet streams that can occur. And then we're going to talk about the atmospheric and ocean interactions. So, jet stream. What are the roles? Okay, so there are looping patterns of air. The jet stream plays an important role in global heat transfer. The cause of the jet stream is a sudden change in pressure by a sudden change in temperature. This sets up a steep pressure gradient that intensifies the wind speeds. So let's develop a model or a 2D model for this. And if you can see this, we have two things. We have the polar front here, right? We got cold air here, got warm air here. So as you come along and look at this 500 isobar line, right, you'll see that and this minus 20-degree temperature line. If you follow them, you see how on the warm air they're much higher than on the cold air side. So you get this steep temperature gradient right here, the red line, and you get this steep pressure gradient right here, and right where they intersect is where the jet stream should occur. All right, another cause. Well, we're going to talk about this thing called angular momentum. And by the definition of angular momentum, all objects have a mass, and that object can be moving, and that object can be moving around a certain point. The distance from that point to where the object is called its radius. And what we're going to do is apply the idea of conservation of angular momentum. So the example I'm going to give you is a figure skater is spinning. What does the skater's spin? It says, when does the skater spin faster? With her arms extended, her arms close to her body. Well, she spins faster when her arms are close to her body. And I'll show you this demonstration in class that will verify that. You guys need to remind me to do that. So what's causing the jet stream speeds to be so fast? Well, if you'll remember, we've got the radius of the Earth here, right, at the equator, and the air is moving around as the Earth, because the Earth is rotating, right? So it's moving here with some angular momentum, which we can get some parcel of air and get its mass, and it's moving with some velocity v at some radius r1. Well, as we've talked about, this air is at the equator, it's rised up, it's at the top, it's got to move farther north or farther south. But you'll see if it moves farther north, its radius is getting smaller. And conservation of angular momentum requires the value of this angular momentum to stay the same before and after. Okay, so it can't change. So since the r is getting smaller, the mass of the parcel of the air can't change either. So the only thing can change is velocity. So to keep the same value, since r is getting smaller, we have to have a much higher velocity. Okay, this is why the jet stream air is getting much faster. All right, there are some other jet streams. Every now and then the jet streams will, the atmosphere will create some jet streams. One of them is referred to as the tropical easterly jet stream. Usually forms in the summer near the tropopause above the Southeast Asia, India, and Africa. Again, large air masses get warmer much faster in the summer than the oceans, so the atmosphere is trying to distribute that excess heat somewhere. And then we have what's called the stratospheric polar night jet stream. Again, yeah, we're in the polar regions, and at night the sun goes away. Usually in most polar regions during the dead of winter, the sun completely goes away, and so the air gets much colder, and we have this steep temperature gradient, and it develops this jet stream to transport the cold air to the warmer climates. And then we get these low-level jet streams. You can get a low-altitude jet stream that forms over a temperature inversion, typically forming at the night over the central plains of the United States. Again, what's causing this? Well, the sun's gone away, remember? And when the sun's gone away, the landmass is going to radiate its heat upward. It's going to get cooler faster. You're going to have a steeper temperature gradient, and these jet streams forward to transport this air to different locations on the Earth, because what the global weather system wants to do is get everybody to the same temperature. All right, so let's talk about some atmospheric interactions with the ocean. So we've talked about the wind patterns, and the winds blow over the ocean, which will cause the ocean water to drift. And if you look at these wind patterns, they line up really close to the ocean currents. So the winds, the global wind patterns actually affect the global ocean currents until the ocean hits the land, and then, well, it can't go through the land, and so it's got to divert itself around the land. But it looks pretty good. You got these, remember, down here you got the geostrophic winds. Look at the direction of the ocean currents, which is the reddish or pinkish lines down here. They're in the same direction as the wind patterns. How does the wind flow around the high? Look at these, flows this way. How's the wind flow around the low? Flows this way. Look at the ocean patterns. They're generally in the same direction. So we have this atmospheric ocean current linkage that is going on, or interaction. All right, so because of the large frictional drags we have in water, water is much denser than air, so it has a much greater drag force or frictional force that goes on. The ocean currents move much more slowly, and you'll see the red arrows here are warmer currents, and the blue arrows are the colder ocean currents. And again, the ocean is trying to move the warmer water to the colder regions and the colder water to the warmer regions to equate the temperature of the planet. All right, so the major ocean currents do not follow the wind patterns exactly because they got the land masses are in the way. But what they do form is these semicircle patterns or circular loops, and we call these circular loops geys. And those are come very important to mix the water in the ocean. So the ocean currents cause the different temperature waters to mix. We need that in order to equate the temperature. And every now and then, where a cold ocean current meets a warm ocean current, you get a boundary. And we call these boundaries of different temperatures and densities of the ocean water, they're called ocean fronts. And here is a color-enhanced picture of the Gulf Stream. So here's Florida right here, and here's the United States East Coast, and you can see the warm water coming from the Caribbean going up the East Coast this way, and you can see a couple geys right here. So here's one that's ending because there's a little bit of cold water breaking off. Here's another one right here. Here's another one forming right here. So we're having all this mixing. You can see the cold water coming down the Atlantic coast from the poles here. And you can get all this ocean atmospheric interactions. All right, so I hope you have a better understanding of the role of the jet stream. I hope you have a better understanding of another model for the creation of jet streams. Other jet streams can form, not the ones that are in the boundaries between the two global convective cells and mechanical convective cells. And I hope you have a better understanding of the wind and ocean interactions, or atmospheric and ocean interaction. And I'll see you in part 4.